How many people have seen or are planning to see August solar eclipse? Awesome. Okay, so of you, how many people are going to their first eclipse in August? Awesome. All right. So the last question is, how many people know who Dr. Drake Ramore is? Dr. Drake Ramore up there. He's on their board there. Dr. Drake Ramore. You guys don't know Friends? Friends?
Oh, yes.
Joey plays Dr. Drake Ramore. So normally I'm a solar astronomer, but for my first slide, I'm going to play a psychiatrist because Joey can play Dr. Drake Ramore. I can play a psychiatrist. A total solar eclipse is a really emotional experience, and people have wondered why do people get so crazy during a total solar eclipse? So I'm going to present to you a theory with evidence, and hopefully you'll buy it. So the first thing that you'll see at a total solar eclipse is the corona of the sun. The corona is the outer atmosphere of the sun. It's heated to 1,000,000 degrees Kelvin. It's sculpted by the magnetic fields in the solar atmosphere, and it's just, it's just goddamn beautiful. It's the most beautiful thing we see in the sky. I'm biased, but I think it's true. Second thing is the sun goes away. It's the middle of the day, and the sun goes away. So if you're a rabbit and the sun goes away, it's not going to end up well for you. You're going to get picked up by a hawk, and that's all she wrote, right? So I think there's something primal in the back of our brains when the sun goes away in the middle of the day that makes us sort of have a fearful sort of feeling. And I think this combination of seeing this beautiful, awe-inspiring corona with this weird, primitive fear makes people go a little bonkers. So I'm a scientist and I have evidence, okay? I did the best research anyone could do. I looked at YouTube, and I'm going to present my evidence to you guys to support my theory. So India, Exhibit A, India 1995. Hopefully YouTube will work. I hope you guys can hear that. So people are yelling. China, 2008. Where the damn? All right, yelling in Chinese, Mandarin, and then it gets louder. All right, maybe just one more. Norway, 2015.
Lots of ways to do it.
Oh my God.
Okay, so that's yelling in Norwegian.
Yeah, I know.
So it doesn't matter what language you speak. It doesn't matter if you live in the desert or in the Arctic or in the jungle. People really experience these emotions when a solar eclipse happens, and some of them will go bonkers. So for those of you who are going to the next eclipse next month, be prepared. You might be going bonkers as well. Besides the emotional experience, there's science that happens too. So what happens during a solar eclipse? Well, the moon blocks out the bright part of the sun. So if you're in your house and you take your thumb and you block out the light in your living room, you'll see dust floating in the air in your room. Hopefully not as much dust as in that room, but you'll be able to see that. And that's exactly what's happening during a solar eclipse. Sunlight is bouncing off of electrons and particles in the corona and is being scattered into your line of sight, into your eyeball. You can't see that during the day because the sky is so blue, but when the moon blocks out the sun, you can see it, and that's the corona, and that's what we're going to study. Now, an eclipse happens about once every 18 months. It doesn't happen every month because the orbit of the moon is slightly tilted. So sometimes the shadow goes below the Earth, and sometimes it goes above the Earth. But when conditions are just right, the shadow will cross the surface of the Earth, and in that little dark area called the umbral shadow is where you see a total solar eclipse. Now, the moon doesn't care what part of the Earth is facing it. It's like a honey badger, it doesn't care. So this leads into the trivia section of the talk. So question one, what fraction of the total surface area of the Earth is covered by the USA?
Raise your hands.
Raise your hands or else you'll be disciplined. What fraction? You guys can't answer. Somebody in the back?
You're back there? How much?
in percentage.
Shout it loudly.
How are you?
Not 8. No, not 8.
5%?
Not 5.
10%.
1%?
Not 1.
10%.
More.
What
What do you
one?
got?
Not 5.
What?
How are you?
8%.
Not 3.
Two.
Do I hear 2? 2.
You got
2 winners.
I heard. I promise.
2%. So the United States covers 2% of the surface area. So we have prizes.
I wasn't trying hard.
So as you might expect, this means that there will be very few solar eclipses visible from the United States because we're only covering 2% of the surface area of the Earth. So the next question, and a related question, is when was the last total solar eclipse that crossed part of the lower 48? Not 1974.
1918.
1918 was a bigger, but not the most recent one.
1972. 76.
No, not 76, not 72.
What are we here? 93?
No, not. It's 19 something.
80 something?
Hey guys, raise your hands.
78. 79, 1979.
Who said 79?
Mike Farrell. Yes, thank you, Mike. And I kind of really wish I could show you the video of the sound. But I'll just link to it and I'll try to do my best Frank Reynolds impersonation. Oh, this is good. So what Frank is saying is that way off in the distant future, when we have flying cars, 38 years from now, we'll have another total solar eclipse in the U.S. And so here we are, a month away.
With the trains.
So the 1979 eclipse crossed the Pacific Northwest and went across Canada, but the eclipse that we're about to see is going to be much different. So the eclipse next month just covers the entire country, and it's an awesome event. So, first of all, the shadow of the moon enters Oregon, goes across the Midland, leaves the continent in South Carolina. And so you can see that the path of totality, the place where you can actually see the corona, is only about 70 miles across. The rest of the continent will see a partial eclipse, but only in that 70-mile swath will you see the corona and a total solar eclipse. So because the path doesn't go over Siberia and it doesn't go over the ocean, we thought, well, we can access this path at many locations along the route, where we can take data. And this is something that's really unheard of. And this is where the insanity began. And I started to think about actually doing that. So we invented this thing called the Citizen Continental America Telescopic Eclipse Experiment, or Citizen CATE Experiment. And since then I've been told there's a movie that sounds something like that. I'm not sure. But if you're in Rosebud, Missouri, right along the path there, you'll see the corona for only 2.5 minutes. However, the idea is that you have stations all around the path of totality, and each of them collect 2.5 minutes of data, and then you splice it together, you'll get 90 minutes of data of the inner corona. So that's what we're planning, is to have these stations along the entire path. We've got 68 plans, and volunteers lined up to take data. Let's zoom in on Idaho. So I'll be in a little tiny town called Weezer, Idaho.
That's where I was. That's where I was.
Right there. Weezer is a tiny town, population of 5,000. And the idea is that the shadow of the moon crosses Weezer, we'll be taking data, and then the shadow will cover the next site in Crouch, Idaho.
All right.
Before the shadow leaves our site in Weezer. And similarly, in kind of the relay race, we'll take data chasing the shadow from our ground stations as it crosses the entire country. So for 93 minutes, we'll have data in this region of the corona that it's really hard to observe. Here's a list of people that are involved. It's a cast of thousands, they're actually hundreds. We've got 27 universities, 22 high schools, we've got people from 8 informal science education groups, and then 4 national labs. So we've got people from middle school age up to professional astronomers. We've got people from tribal high schools in Wyoming and also in Montana. So we've got a huge age and gender and ethnicity diversity in our project. So we've got a huge group doing citizen science, but the real question is, can citizen science really compare with the pros? Okay? So here's what we're doing on Maui, on Haleakala. We're building a 4-meter diameter solar telescope. It'll be the biggest solar telescope on the planet. It's called the DKI Solar Telescope. We're scheduling the first flight, or we're hoping to see first flight in 2020. So you can imagine a 4-meter diameter magnifying glass. First of all, you can fly a lot of ants with that. But also, it's going to give you a really close-up view of the sun. Our telescopes for the CATE experiment are only 3.5 inches across, 80 millimeters. So can we really do science with 80 millimeter telescopes? That's the question. And the answer is yes. And the reason is because in the path of totality, the sky is really special. It's very dark. We looked at 30 different sites around the world to put our new Eclipse telescope, and we selected Haleakala because the skies are really dark there. And you can see in this image, it's nice and blue. But during a total solar eclipse, the sky is 10,000 times darker, or 100,000 times darker. So if we take our 80 millimeter telescopes and move them to the special conditions in the path of totality, they're equivalent to having a 1.3 meter telescope on the top of Haleakala. So something that's pretty significant compared to even the biggest solar telescope on the planet. So we think we're going to do a great job collecting new and interesting science. But, so doesn't NASA do this already? People with NASA t-shirts, don't you guys do this already? No? Nobody? NASA does, but they don't do it in this area. So what NASA has learned, the trains go by. What NASA has learned is that they can image the solar winds coming out of the solar atmosphere. So here's a movie sequence from October of 2003 showing the solar wind in this corona. You'll see smaller particles moving out, and then you'll see these solar storms that erupt from the sun. If it's pointed in the right direction, you'll see a big donut coming at you, and then the electronics in your spacecraft get destroyed. Like that.
Oh, awesome.
This is called space weather. And so this has a real impact on the Earth. This can also cause problems with power and knock down power grids. It can damage satellites involved in banking systems or in communication systems or GPS. Who uses GPS, right? Turns out we all do. So we really want to be able to predict when solar storms are going to hit. And just like if you're trying to predict when a monsoon storm is going to hit and what particular part of Tucson is going to hit, you need to understand the wind pattern around Tucson, right? We try to understand the solar wind pattern to understand how solar storms propagate through the solar system and the environment. If you remember, there's a little black donut. There's a data gap in the NASA image. Let me show you. So it's this guy here. It turns out it's really hard to see that part of the corona, and you can't actually see it from space. So in this data gap, of course, all the interesting science happens. The solar wind accelerates. It's going at something like a mile per second slow at the surface of the sun. And up here, where we can see it, it's going at about 200 miles per second. We don't know how it does that. So what we're trying to do with the CATE data is understand that acceleration. And so all of you guys accelerated today, right? Where you got on the freeway, on the on-ramps, you're going really slow at the bottom of the on-ramp, and then you push the gas pedal and added energy to your car, and you accelerated up to freeway speed, 60 miles an hour to merge with traffic. That's exactly what the solar wind is doing in this area, in this data gap, but we don't know how it's doing it. We don't know what's providing energy, what's putting its foot on the gas pedal. So that's what we're trying to do. My friends at NASA are trying to do that as well. And here's the best result today. Here's the edge of our field of view. Our CATE experiment will look at this yellow area in this graph, which plots speed of the solar wind versus distance from the sun. So up here you see it's going at a really high speed, 200 miles per second basically, and here the sun is going at a very low speed. But in here, I think my colleagues are just making stuff up. I mean, they're scattered a factor of 100 between different data points. What we're going to do with our eclipse data is make about 700 measurements in each of these structures that we're going to see, and cover this region with an error bar 6 times smaller than the error bars on this. So I think the CATE data is going to revolutionize our understanding of the solar wind near this area of the sun where the acceleration is happening. So in summary, what a solar eclipse does is it opens up a window. So here's the NASA field of view that we get with the data gap. And here's our eclipse data from 2016 from Indonesia. Superposed on that and rotated to fit. So in the CATE experiment, we're going to look at the solar wind in this area and measure it. The things that we're sure we're going to see, you guys going to the eclipse in August are going to see these things called polar plumes. So above the north and the south poles, it's a little bright, but maybe you can see these faint streamers. You'll also probably see some streamers along the east and the west sides of the sun. So we're going to focus on these polar plumes. They're kind of like magnetic straws, and the gas is flowing in these magnetic straws. And what the CATE data will show us is how fast it's going up along these straws. So imagine sitting across the table from a friend who's drinking a milkshake, and you're watching the milkshake go up this straw, trying to measure the velocity. That's exactly what we're going to do with the data that we're going to collect from the eclipse. All right, so have we done this before? Why do we think we can do this? Well, we tried. And back in 2015, we had a lone volunteer, Fred Isbiner. We traveled to a faraway island called the Faroe Islands. He was from Illinois, from Carbondale, Illinois. He practiced during a one sunny day when it was sunny in February in Illinois, here. Then he set up a tripod in the rain in the Faroe Islands. And then he put on his parka and tried to look in and got 30 seconds through clouds. And this is the image that we got. So it was a little inspiring, but also a little depressing. But in 2016, we had a bunch of rock stars take data, and they're here actually. You get their autographs after. We got students from 4 universities who we shipped off to Indonesia in March of 2016. And we set up a network of 5 sites. We also had Fred Isbiner and a group on a cruise ship in the middle of the Makassar Strait. So we got data, and I'll show you some of it. Some of it's really excellent. But we found out, perhaps more importantly, we found out what could go wrong. I mean, these guys are halfway around the world, and we had them stuck with crummy software. I apologize. We fixed that, and we think we understand the focus issues and other problems as well. Anyway, here's some of the best data that we took. Here's just a raw frame, and if you take a picture of the eclipse, your picture is going to end up something like this. Not so thrilling. What we do with the CATE experiment is we take a sequence of 8 pictures and then combine them into an HDR, and then filter it, and the pictures end up more like this, where you can see the structures in the corona. From the limb of the sun out to here, the brightness drops by a factor of 1,000. So this is really a lie, but it really approximates more about what your eye will see when you look at it visually. So here's the one way of filtering the data. Here's another way of filtering it. It's on the poster, so we've got some high spatial frequencies, and we can see the magnetic loops that are controlling the plasma. And then if we go really crazy, we can do this, which is to look at the edges where the magnetic fields really control the dynamics of the gas there. It'll take some special beer to see this during the eclipse in August. Let me know if you see it visually, okay? So, the plan is that after these guys came back from Indonesia, now they've got on-the-job training and they're experts. So we had them train our 70 volunteers for the 2017 eclipse. And we're going through the same process, right? We're not going to reinvent something after it worked. This is what we did in Indonesia, and we published the paper. Right now we're doing follow-up research. Same thing for 2017. Especially last-minute problems. You know, I'd be disappointed if we didn't have last-minute problems, right? So we're trying to put out those fires right now, like, oh, the camera's overheating. It's 102 in Tucson. But hopefully, we're right here, and in the next couple of weeks, people are actually going to travel to other sites and start to take data. So, our Rockstar students have gone through and taught all of our volunteers in a sequence of 11 training workshops from Oregon to South Carolina. You can see the variety of the conditions. We had snow in Wyoming, and in Tucson at Cienega High School, it was 100 in the shade. So we tested the cameras under a lot of different circumstances, and with a lot of different people. Right now, they've brought their telescopes home with them, and they're practicing at their houses. And so Todd showed us Pluto shine on the moon of Pluto. Here's Earth shine on the moon of the Earth. Turns out that Earth shine has about the same brightness as parts of the corona. So we're practicing both on the sun and the moon. And actually, if you look at the sun tomorrow with some eclipse glasses, you can see a pretty big sunspot with your naked eye. It's hard to see visually, but it's visible. So check it out tomorrow morning. One of the things that made this program really challenging is that we assigned the funding so that people keep their telescopes after the eclipse. So on August 22nd, we're going to have 68 groups across the country that have telescopes and they're trained to use them. And I know that there's some astronomers in the audience, right? You don't have to identify yourself, it's okay. But I know you're out there, and if you can think of projects that a network of 68 telescopes can address, come and talk to us, because the telescopes are just normal telescopes, 80mm telescopes with good detectors. And I think it would be exciting to have this group who's excited by the eclipse now become more engaged in citizen science and astronomy. So that's the Citizen CATE experiment. Now for the bad news. If you're staying in Tucson, Tucson is about as far away as you can get from the eclipse path. Maine parts of, guys that live up here in Maine, they'll be further from the eclipse path than we will be, but we'll see about 66% coverage. So you'll definitely need some eclipse viewing glasses like these. And trust me, you can't see anything when you put these on. Nothing. I've got a couple of hundred up here, so after the talk, please come by. If you have 5 or 6 friends, take 5 or 6. But please make sure that there is something for everybody. It starts at 9:15 in the morning and ends at lunchtime. So take time on a Monday to get out of the office and take a look. Now, if you absolutely can't get out of the office, NASA is going to live stream the event at this website, so you can watch it on the internet and hopefully on evening news. Our plan is to have a rough cut movie of our data that Monday night, because that on Tuesday there'll be a tweet from someplace in DC, and everyone will forget about the eclipse Tuesday morning, right? So Monday night on the news, we're hoping to have our data for you to see. That's all I've got. Hopefully these sites can help you.